Hi, I'm Seonyoung Park from Sungkyunkwan University, Republic of Korea, and our paper, Never Too Late to Learn, Regularizing Gender Bias in Coreference Resolution, is about how to mitigate gender biases, especially in transformer-based pre-trained language models. And pre-trained language models have gained huge popularity among AI researchers since it can be good initializers for efficient transfer learning. However, as most of the pre-trained language models are trained on massive text datasets, they do not only learn how to effectively observe the linguistic features, but also replicates the stereotypes from the datasets. So in this paper, what we basically want to do is to make the PLM lose its internal bias and show that it is never too late to adjust the pre-trained language models in the fine-tuning phase or in the later training phases. And among various societal biases, we focus on gender bias issue, particularly focusing on co-reference resolution task with the scheme of gender pronoun resolution. So in GPR, given a context, models have to predict the appropriate gender pronoun for the referent. And the GPR predictions can be interpreted in two ways. Pro-stereotypical predictions are the ones that are in line with the perception of the real world, and anti-stereotypical predictions are the ones go against the common stereotypes. So given no linguistic context, the result of GPR tasks is regarded as ideal when the model can make the pro-stereotypical and anti-stereotypical coreference decisions equally. And GPR can reveal two types of gender bias problems, which are stereotype and skew. Stereotype is the unequal assignment of gender pronouns to stereotypical professions, and skew is the model's preference of assigning certain genders pronouns, usually masculine pronouns in the real world, due to the male-oriented large-scale datasets. So with the sentence, Mask is a doctor and has high salary, if the model predicts the Mask token to be he with a high probability, we can assume that the model has learned that the profession doctor is often considered a male's job, or it just learned that it can gain higher performance by predicting the masculine pronouns based on the gender distribution of the training corpora. So for bias evaluation, we follow the previous work and take the F1 score-based measures. And stereotype is calculated by the F1 score difference of pro-stereotypical and anti-stereotypical professions. And in the past, there has been gender-preserving debiasing approach. And what they did was to define a gender subspace in the word embedding space with the gender inherent tools, such as brothers, sisters, mother, and father, that should have gender information in the embedding space. And they projected embeddings of the gender-neutral words to the gender subspace and trained them to be orthogonal. That means that they can be distanced away from each other. And we find this approach very interesting, but it was only examined in steady word embedding setting using the word-to-vec and glove, so we decided to take a step further in our paper. And for skew, which is the tendency of the PLMs to make dominant predictions on a specific gender, it is calculated by the F1 score difference of male and female stereotypical professions. And online skewness mitigation was suggested to normalize the probability of a masked pronoun being predicted in an occupational context and by dividing it with a prior probability of choosing that gender in an unoccupational setting. However, it is a kind of a post-processing mechanism. So in this work, we aim to focus on making the PLM itself to be more unbiased. And for our work, we take two well-performing approaches, which are data augmentation and GPR fine-tuning. Data augmentation is to add the gender-reversed version of each sentence to the training corpus to make it balanced. And in GPR fine-tuning, when given a masked input sentence, the model is trained to predict the correct gendered pronoun for the masked token, as in the traditional masked language modeling task. While these approaches are very well known to handle the skew problem quite effectively, they do not directly address the stereotype problem and the degradation of the model performance of the debiased models. So we suggest two more ways to deal with the problem. And first one is the stereotype neutralization method. It is to alleviate the gender characteristics retained in stereotypical words using a gender directional vector during the fine-tuning step. So before fine-tuning, we predefine the gender directional vector by averaging the embedding difference between male inherent and female inherent terms. And then we add a normalization step to avoid error fluctuation during fine-tuning, and then we take the embeddings of stereotypical occupation words and make them orthogonal to the gender directional vector, and then make them orthogonal to each other. Second one is the elastic weight consolidation, EWC, and it is to preserve the important parameters of the PLMs. Since the PLMs are trained on the augmented data set, they tend to underperform on ordinary NLU tests. So we try to prevent that from happening to a certain degree. In EWC, we calculate the Fisher information using the original pre-trained language model. So in our case, BERT-based uncased. And for each layer, the model training is affected by the parameter difference between the two models, the one getting debiased and the original PLM, depending on the importance of the layer. Then we combine the approaches all together to obtain a model that can perform well on both debiasing and NLU, and we name the model BERT-ASE as we only use BERT for our experiments and analysis. And in addition to the methods, because the previous F1 score-based metrics can only capture the correctness of the model's prediction, we propose a new probability-based stereotype quantification score, and it is based on the variance of low probability of assigning the gender pronouns for the pro-stereotypical occupations. For GPR fine-tuning, we take the English version of Onto-Notes 5.0 and augmented it to have both examples with two genders. And then after fine-tuning, we evaluated the models on window bias type 2 sentences, a data set for GPR. And for measuring bias, we obtained all three metrics, stereotype, skew, and SQ score, where lower values indicate that the model is well debiased. And using the gender-neutral examples, like the developer argued with the designer and slapped a mask in the face, where there isn't no certain answer for the sentence, the BERT, without fine-tuning, showed relatively high skew, stereotype, SQ. In the fine-tuned model on unaugmented data set, they showed relatively slightly lower in F1 score, but it still had high SQ score. Moving on to the models with the data augmentation, BERT-A and AO, they achieve lower skew and SQ score compared to the previous models. However, both the models gain the high stereotype, which indicates that data augmentation cannot solely handle the gender bias problems. On the other hand, last but not least, our proposed models using SN and EWC effectively mitigated the stereotype problem while having low SQ score and skew. We want to point out something about SQ score. We observed that the results align with the results of SQ score align with the major hypothesis we set for the work. First, drawbacks of transfer learning using PLMs, and secondly, the importance of balanced training corpora. As you can see, the models with data augmentation have much lower SQ score, and we think it backs up our hypothesis to a certain degree. And we also evaluate the models on the baseline GPR task, which consists of sentences with gold labels and verified if they can predict the correct pronoun. Our model BERT-ASE outperforms BERT-A and AO for men and women and is similar on the Alice and Bob examples. So overall, we think that BERT-ASE can adopt the benefits of each regularization term very well, and they mitigate the biases and maintain the baseline GPR performance compared to other previous debiasing mechanisms. And by comparing the mask topologies and visualizing the embeddings, we could see that our model can predict with less stereotypical misconceptions compared to the pre-trained BERT-based uncased. So to conclude, our methods tackle the gender biases coming from the data sets. However, we still have to figure out some issues that might bring concerns in the future, such as performance debiasing trade-off, or how to define the scope of gender besides the binary settings, and also how to deal with the multilingual settings where there are more than two types of gender pronouns to be exact. And with the mentioned issues in mind for the future work, we aim to expand our perspectives so that our methods can be inclusive to all types of genders and languages and be effective in other downstream tasks as well. And this is it, and thank you for listening.